Hello and welcome. In this video we're going to take a look at slope fields. So slope fields are another qualitative method that allows us to visualize and understand better what's happening to the solution of a differential equation. So slope field is exactly what it sounds like. It's a field or a space filled up with slope vectors. So one of the things that we know, if we can't solve a differential equation, or the differential equation might be too hard to solve, or we just kind of want to get a sense of how the solution behaves, we can really take advantage of what dy dt is. So dy dt, this symbol represents a slope, and we know that out of any given differential equation, the input is, or the inputs could be t and or y, and the output is a slope. So geometrically, a slope can be visualized by a line segment that has a steep or not so steep incline, or a steep decline, or not so steep decline, or anywhere in between, of course. And so every time we generate a slope for a given input, we can, at that ordered pair on the ty graph, sketch a small vector that represents the slope at that point. Let's go ahead and take a look at this very first example that we have here. So we have a slope, we have a differential equation, and we want to sketch a slope field for t over the interval 0 to 2 and y over the interval from -1 to 1 at each of the integer points in this region. So of course the reason we're saying this is because there are infinitely many points even from t equals 0 to 2. So if on this graph I label this as t equals 1 and t equals 2, and then y goes from -1 to +1. So we are only focused on values on these four integer points, but we'll have a point here, a point here, 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 and here. So a total of 9 points that we want to look at in order to represent the integer pairs in this region. So in order to figure out what the slopes are at each of these 9 points, it might be helpful to first create a table. So at every ordered pair, I want to consider the t and the y, and then calculate dy dt. And on first sight, you see that this equation does not have t in it, which at first can be confusing, but if you simply write it as 2y plus 0t, the observation is that t simply does not contribute to the value of the slope. However, it is there, it's just invisible, and if it gets multiplied by 0, it does not really matter what the value of t is in this equation. So if I start off arbitrarily at the point 0, 0, in the ty plane, that's going to generate a 0 slope. Okay, well a 0 slope is a horizontal line segment. So I'm not going to draw this horizontal line segment all the way across. I'm just going to draw a little tiny line segment here that has about a 0 slope and that points to the right, because of course we know time increases, does not decrease. Therefore we draw a directed arrow to the right with a slope of 0. So the incline of that little segment is 0. We would do the same thing at the other points, and let's go ahead and jump to the point 0, 1, which is this point here. When t is 0 but y is 1, dy dt is twice the y value, so 2 times 1 plus 0 times 0 is 2. And we can now generate a little slope segment at this point that has about a slope of 2. Now here would be, if it pointed right over here, that would have a slope of 1, but there's a point up here that it actually aims towards because it has a slope higher than 1, so I'm going to draw a little segment that looks like that. And I'm going to repeat this for 0, -1. And for 0, -1, if y is -1, then dy dt is going to be -2. So that's going to be similar to this slope vector except pointing downwards. And I'm going to continue this way. So we'll start off with 1, -1, and in that case dy dt will still be -2, which at this point here will have exactly the identical slope vector as we had just to the left of it. So keep in mind that the t value is not influencing where we are on the t-axis, does not influence the slope segment. We only are concerned with the value of y. So in fact, what we're going to see is that if you look at the t value of 1 and the y value of 1, that's going to be exactly identical to what we achieved up here, because as long as y is 1, dy dt is going to be 2. And so at the point 1, 1, I should probably be careful not to make those look negative. I'm just trying to illustrate that this point here and at this point here are going to have exactly the same slope. So at the point 1, 1, I'll have exactly the same slope that I had at 0, 1. And if I look at 1, 0, well, that's going to be the same thing as 0, 0. So I'll make a little symbol here, a little square, to show that these two will have exactly the same slope, because once again, the fact that t changed does not influence the outcome of the slope. And so this is going to have a slope of 0, and so we should see a horizontal line segment here. Now I'm not going to repeat this for the remaining 3 points, but we should see that if I maintain a y value of 0, I'll maintain a slope of 0. If I maintain a y value of 1, I'll maintain a slope of 2. And if I maintain a y value of -1, I'll maintain a slope of -2. So what we see is that these 4 slopes here, or these 3 slopes here, are the same. These 3 slopes here are the same, and these 3 slopes here are the same. But for any given value of t had no impact on that slope segment itself. So we kind of have these rows of vectors that look very, very similar. Well, what does this allow me to do, though? What did I gain here? One of the things I gained is a good visualization of what an initial condition is expected to do. So we don't have enough densely populated vectors here, but it sort of appears that any initial condition that starts off in the first quadrant, like that one, will somehow veer upwards. We don't exactly know how, but it looks like, and if we were to plot more vectors, these ones here would just be pointing upwards, but a little more steep. And if we start with an initial condition down here, it looks like that initial condition may end up veering downwards. So think about these as wind vectors. If you put a feather in the wind, these vectors kind of illustrate where that feather is expected to blow based upon where the wind is going. All right, so let's take a look at a little observation here. What can be said about the pattern for slope fields that are autonomous? That is, that only depend on the value of y. Well, what we should see is that the slope vectors are the same for a given value of y, independent, I can spell this, independent of the value of t. So what we kind of describe this as is we should have rows of similar vectors, I shouldn't even say similar, of identical vectors. Great, and one other thing that we see here is that we have also an equilibrium point. When y is 0, regardless of what the value of t is, if y is assigned to be a value of 0, then dy dt will always be 0. And so one other trajectory that we see here is that if you start off with a y value of 0, you will always have a y value of 0. And this would make sense in the context of things like populations, where you can't create animals out of a lack of animals. Let's also take a look at one that depends exclusively on t. And this is something that we would have seen in our Calculus 1 class. And once again, let's just go ahead and look at these for t between 0 and 2 and y between -1 and 1. So once again, we're basically going to be looking at the slope at 9 different points. And I'm going to jump the gun a little bit here to observe this pattern, but as long as I'm maintaining the same value of t, regardless of what the value of y is, that should not change the slope. So I'm going to write this as 2t plus 0y. Again, for that purpose of seeing that the value, as long as t maintains a constant value. So when t is 0, that's these 3 points here. So 0, -1, 0, 0, 0, +1. all three of these ordered pairs, 2 times 0 will be 0, plus 0 times whatever y is, will still be 0. So we cannot call these equilibrium points because equilibrium points are the value of the dependent variable, but all three of these vectors would point horizontally. Now, when t becomes 1, and I look at 1, negative 1, 1, 0, and 1, 1, 2 times 1 is 2, so for all three of these points we're going to have a slope of 2, which I'll just kind of draw like that. And then when t becomes 2, 2, negative 1, 2, 0, and 2, positive 1, 2 times 2 is going to be 4, so these are just going to have twice the incline of the slope. I'm going to try my best here to just make it look more vertical, but hopefully you just get the idea that all three of these are the same. So once again, we see that these three are the same for that value of t. And when we change the value of t to 1, all three of those vectors are the same. When we change the value of t by 1, all three of those vectors are the same. And for an initial condition, one thing that we can observe is that it looks like, regardless of what the initial condition is here, it'll kind of start off a little flat and then start to pick up with more speed. Then anything below it will do pretty much exactly the same thing. And anything below that will do pretty much exactly the same thing. And so what we can think about these as is these are vertical shifts. So when you solve an equation like this, observe that we would get t squared plus c would be the solution, and that just emphasizes that every single initial condition will just be a shift of the same curve. Back up here, what we should notice is that within one region, like for example, when y is bigger than 0, all of these curves would behave exactly the same way, and they would all be sort of these horizontal shifts. So for that same initial value of y, but for a different t, we would just notice that all those curves are exactly the same. They're parallel, but they're, I shouldn't say parallel, but parallel-ish because of the fact that they are horizontal shifts. All right, we'll leave it at that. And so what can be said about the pattern here? Well, the slope vectors are the same for a given value of t, independent of the value of y. So in fact, I'm not going to even rewrite that. I can just copy and paste this, because copying and pasting is fun after all. And the slope vectors are the same for a given value of t, independent of the value of y. So here we notice we had columns of identical vectors. That is, we could circle one of these columns and see that all three of those behave identically. All right, let's look at one now that has both t and y in it, and the coefficients being non-zero. Again, we look at these slopes for t between 0 and 2 and y between negative 1 and 1. Now here we kind of do have to plot vectors at each of those 9 points and look at them independently, because anytime we change t or y, we're going to change the value of the slope. So here I'm just going to go ahead and write out this entire table, and it's going to be the difference between half of t and half of y. So if I start down here at 0, negative 1, that's going to give me a slope of, let's see, 0 minus a half times negative 1 is going to be positive a half. And I'm just going to continue doing these. So 0, 0 will give me a slope of 0. 0, 1 will give me a slope of negative a half. So that means that negative a half, so that would probably look something like this. It'd be positive, oh sorry, that's down here though. That's down here at positive a half, so I want it to aim right about there. You can see this gets very tedious now. 0, 0, there's a horizontal slope. Here there's a negative slope. Negative a half, I want it to aim right about there. And now when I change t to 1, I'll look at 1, negative 1. 1, 0, and 1, 1. So at 1, negative 1, that will be a half plus a half, which is 1. This will just be a half, and this will be a half minus a half, which is 0. So those slopes will look more like this. So at 1, negative 1, I'll have a slope of 1, so it'll aim right up there. And here I'll have a slope of a half, which will aim right about there. And here I'll have a slope of 0, which will look horizontal. And finally, we look at when t is 2. So we'll look at 2, negative 1, 2, 0, and 2, positive 1. So when t is 2, that's going to give me an output of 1 for 0.5t. When y is negative 1, that'll give me an output of positive 0.5. So this should be a slope of 1.5. This will be a slope of 1, and this will be a slope of, let's see, 2. It'll be 1 minus a half is going to be a half. So at 2, negative 1, I'll have a slope of 1.5, which means I want to aim for right about there. At 2, 0, I'll have a slope of 1, which will aim right about there, a little less inclined than that one. The slope of a half will aim more horizontally, less vertically. And I can already kind of see what's going to happen to an initial condition. If I pick that one, gosh, it looks like it might even do something like, this and then come back up. And then maybe an initial condition here will probably start to also grow upwards here. These will kind of grow upwards. So it looks like ultimately all of these initial conditions will start to move upwards. Again, this is a very limited picture, so what we observe here is just based on these 9 slope segments. Another thing that we could do to make the slope field more precise is to populate it with vectors even in between the integer values. So there's no reason why we couldn't have looked at the slope at the point, say, 0, positive a half, or 0.5, 0.5. There are really infinitely many vectors that we could generate within this plane. But we wanted to keep this simple since we are doing this by hand initially. So one thing to notice that now that our differential equation depends on both t and y, the slope segments change when either or both t or y change. So we don't see this consistency in having the vectors vertically be the same or the vectors be the same along rows. We now kind of notice that it looks almost like a random scatter of vectors. So slope fields are powerful to help us visualize the solution space. That is, we didn't just look at, we're usually interested in some particular initial condition, but we also get the bonus of seeing how all solutions around it behave over time. It's powerful when it extends broadly, because if you're trying to do a kind of a general analysis or to say, well, how do initial conditions evolve differently, you can see that with the slope field. You don't get the exact solution, and I don't know that this curve swings up as quickly as I made it swing up. Maybe it takes longer, and maybe it's even more flat. Maybe it looks more like this for that initial condition. But again, this is a qualitative analysis. It's just to describe the qualities of the solution. Now, of course, it would become painstaking to sketch not only accurate, but also all-encompassing slope fields. Technology is much more efficient in doing this for us. And there are many slope field applets out there. This is one that's simple and readily available, so we're going to go ahead and use this one. What this one shows you is, first of all, you want to make sure this is set on 1 ODE. We won't use the polar stuff. We'll eventually use systems. Here they use y and x as the dependent and independent variables. To be consistent with our notation, we could use dy dt. And let's just go ahead and plot the first slope field, which was 2y. Okay, so here we have it, and that looks very similar to what we came up with before, but you see that we have, and we want to limit ourselves, let's say, from t is 0 to 2, as we did in our sketch, and y going from -1 to 1. Now, obviously, this has a lot more vectors populated in there, but you see they follow the general behavior. And I could reduce the number of segments that I have along the t-axis. This is 1, 2, 3, 4, 5 columns of vectors. If I just wanted to do, it won't let me do a 3 by 3. The lowest I can go is 5. But there you go. That looks very similar to what we had before. Now, the more slopes we put in there, obviously, might say, well, the more the better, but it starts to get kind of unnecessarily dense. Maybe up to about 30, it looks good. You can also, we'll talk more about this in here, what it means to use Euler, improved Euler. These are numerical techniques. But if I enter an initial condition, like for example, 0, 0, and I press submit, that will actually sketch the solution curve using a numerical method, which we haven't covered yet, but we will in a soon-to-come lesson. I could actually look at different initial conditions in here. Maybe 0, a quarter, which I expect to kind of go up and to the right. Oh, see, my sketch with my cursor was a little bit more exaggerated. And you can also actually click in here, and it will show you where that trajectory goes. So you can see how these curves appear to just be horizontal shifts of one another. If I change this to 2t, it uses those same initial conditions, but with 2t we saw that those are just vertical shifts of one another. If you want to make this more precise, you can change this to Runge Kutta 4, RK4. It's just a more precise technique, and the curves look much more smooth with that. Let's go ahead and take a look at our logistic model. This one would be very painful to have to do by hand, but recall that here in this model we had a growth rate parameter of 0.1, a carrying capacity of 4 elk, and I say appropriately scaled. This could be 400 or 4 million or 4,000, whatever. We don't want to say that you can't have 0.2 elk because it could be in hundreds or thousands, in millions, etc. So to sketch this guy here, I'm going to come over to my slope field and just type in 0.1y times 1 minus y over 4. Before I press enter, the one thing that we should notice is that we're going to have equilibrium points at both y equals 0 and y equals 4. So that means that we should notice horizontally that our slopes are going to all be the same. That means we're going to have rows of very similar vectors, since this only depends on y and not on t. This is an autonomous differential equation. If I press enter now, let me go ahead and clear all the curves. Looks very boring, right? Because first of all, I am looking at a window of populations from y equals -1 to 1. I can't even see the equilibrium point in there yet, but I do see that right at y equals 0, those neighboring slope vectors look very, very flat, which makes sense. So let me change my t to go from, maybe not, if this is years, maybe I want to do 10 years. And maybe for y, I want to go from 0 elk. Let me go from -3 elk. And I'll tell you why in a second, all the way up to 7 elk. So the first thing that we see here is I'm going to change my value of t just because these slope vectors are kind of flat and boring. So let me go up to maybe time 20. There we go. We kind of see more curvature in here. But you see that right at y equals 0, if I pick an initial condition, I could click on 0, 0, but it's not ever going to be able to look at this ordered pair here that pops up. I'm never going to be able to get it close to 0, 0, as close as I want. So I'll just type the initial condition in. Well, there you go. So if you have 0 elk, you're going to have 0 elk for all time, because when y is equal to 0, the rate of change is always 0. So notice that all the slope vectors at y equals 0 are similar. Now maybe I want to also consider, what if I start off with a population of 4? Well, if y is 4, I'll get 1 minus 1, which is 0, and that's going to give me a 0 slope as well. Well, there you go. So if you are at your carrying capacity, you're going to have births and deaths, but you're not going to have a growing population. I'll just click in here to show what that curve looks like. So you have this exponential growth, but it takes a while to pick up, and that could just be due to our slow growth rate. But let me go ahead and change this maybe to time 60. And there we go. There we see that logistic curve. That's where this model gets its name. That's called a logistic growth curve. So you see that the population starts to blow up, but then because of the carrying capacity, because of limited resources, the population is still growing but at a decreasing rate, and the population flattens off as we approach the carrying capacity. Initial conditions above y equals 4, we see that those decay, right, because we're overpopulated, we're beyond our carrying capacity of the environment, so the population is going to want to decrease back to y equals 4. So the equilibrium points very much act like asymptotes. If I pick anything here, I know I can't have negative populations, but what we should see is that the population in that case would decrease infinitely. You can also experiment with this and change this to see, okay, well, what would happen if I doubled the growth rate parameter? Well, that just means that growth is going to occur faster. That shouldn't change the equilibrium points, but watch what happens to this point right here. I'm going to leave my cursor right there, which is about the inflection point, where we go from concave up to concave down. And now you see that that point is shifted over here. Well, that makes sense because the population growth rate is much faster, so we should approach our carrying capacity faster than if we had that rate of 0.1. So that looks like an S, but it's almost as if you horizontally stretch that S. If I make this 0.5 to really make that clear, look how fast it reaches its carrying capacity, and look how fast these things happen. And that should make sense because mathematically what we're doing is we're scaling the rate of change by a bigger factor. If I make this like 10, which is just insane growth, that S is very, very compressed and growth occurs very, very rapidly. We'll talk more about what all these little features mean in here. These are just kind of some models that they have built in, and we'll talk more about the numerical solution table as we go. One last key point here is that, in general, a good strategy for determining what a slope field will look like is to first consider the equilibrium points of that model. So, for instance, given a differential equation such as dy dt equals, we'll just say something like 3 minus y. Well, if I first look at what the equilibrium points of this are, and I set this equal to 0, and I find out that y equals 3 is an equilibrium point, what that already enables me to do in this sketch of this slope field is that I know that if y equals 3, 1, 2, 3, that my slope fields for y equals 3 will all be 0. And now, because this is autonomous, we know that it doesn't depend on t, so t will not influence the rate of change. But when y is bigger than 3, then that's going to give me 3 minus a bigger number, which is going to give me negative slopes here, and when y is less than 3, positive slopes here. So that kind of already gives me some insight into what I should be observing, something similar to this. So first start off with those equilibrium points, even if there are some. A lot of times there aren't any equilibrium points, but at least it gives you an idea of what's going on. So that's it for this video on slope fields. In an ensuing lesson, we're going to get into Euler's method, which is an explanation for how this applet actually produces these solution curves.